So we're going to start the next session soon. So if you could come in from outside or get seated, we'll get started soon to keep things on time. Okay. So this session will be all about new primitives. So hopefully it sparks some interesting, cool new ideas. And to start off, we have Benedikt Wagner giving the talk on FRIDA, data availability sampling from FRI. So take it away.
Okay, thank you for the introduction. Yeah, so this talk is about FRIDA, data availability sampling from FRI. This is a joint work with Matthias and Mark. And you maybe wonder what is data availability sampling. So that's why this talk is in this session. It's a new primitive. And that's also why I will probably spend like more than half of this talk explaining what DAS or data availability sampling is, and then we will see what the results of this paper are, data availability sampling from FRI. Okay, so let's get into it. What is DAS? And in particular, where does it come from? So it comes from the blockchain world, from the Ethereum community, and it's a very important concept in the roadmap of Ethereum. So they soon want to integrate this, and this will be an essential part of their consensus protocol. However, even though it is that important, this is still more like a vague idea or a concept and not a like precisely defined object. And if you talk to different people, they have different opinions on what this thing should be and what kind of properties it should satisfy. And also there are only a handful of constructions. And this is sort of the situation how it was when we started this research. So our idea was, let's take this thing and move it to the cryptographic community. Let's give a precise definition and sort of build precise and solid foundations for this thing by giving definitions and also motivating research on new constructions. And ideally, the Ethereum community would then benefit from this research. So that's why a while ago we wrote this paper, Foundations of Data Availability Sampling, with the same co-authors. And there we did exactly that. We defined this thing as a cryptographic primitive formally with security requirements and syntax and so on. And we analyzed a bunch of constructions and developed new constructions. And if by the end of the talk you are convinced that this is something interesting, then you can look at this paper or you can look at a long talk that I gave on YouTube. Okay, but for this talk, I will just convey the intuition of what DAS is. I will not give the precise formal definition. So let's start with that. What is the setting? So we have a proposer, let's call her Alice. We have a peer-to-peer network running some blockchain, and we have a bunch of clients. And now let's say the proposer holds some block of data. This could be a list of transactions or just any data. And we allow the proposer to encode that data and also to compute a short block header. And then this header and the block is sent to the peer-to-peer network and stored in some distributed way. And the clients, they want to participate in this protocol and participate in the consensus, so they will download at least the block header. But for this talk, we will assume that they are restricted in some sense and they don't want to download the entire block whenever there's some block is published. Okay, so they download the block header, but still maybe in the future they need certain parts of this block because maybe they need some transaction that was contained in that block. So their question now is this data that is associated to that header, is it available? Okay, and so for that, they interact with that network, make certain queries, and in the end, they decide whether it's available or not. So this is data availability sampling, and in some sense, these clients act as a verifier for the statement, data is available, whatever that means formally. And the proposer and the network, we can think of these two entities as being the prover in that system. And so when we look at security notions, we will typically assume that these two, the proposer and the network, collude and behave in some arbitrary malicious way to convince that the clients that the data is available, even though it maybe is not. Okay, so that's the setting. Now, to just get familiar with this, let's look at two naive constructions of how we could do that. So again, we have our proposer Alice, we have the network, and we have the clients. Now, Alice holds some data. This is, say, k chunks of data of equal size. Now, what Alice could do is she could just compute a Merkle root, and that would be the block header. Now she sends the data to the peer-to-peer network. It's stored in some distributed way, and the clients just download the Merkle root as the block header. Okay, so now they want to verify whether data is available. And what they can do now is they could sample random positions and try to download these positions. Now what they would get is the ith chunk and some Merkle path, convincing them that this is consistent with the root. Now the question is this a good system? And I claim it's not, right? So I can convince the clients that this is data is available, even though they will not, and even though it is not available. So how do I do that? Let's say I just delete a single chunk of the data. Then the data is no longer fully available. But the probability that a single query hits that chunk is 1/k. So to get a constant probability of detecting this, you already need to do like k queries. And that's just as good as downloading the entire data in the first place. Okay, so we didn't win anything. And this is because the system has a very bad soundness. So intuitively, some kind of soundness property is what we want. Now let's improve this. How can we do that? We use erasure codes. So let's say, again, Alice has her k chunks of data. And now she redundantly encodes them using an erasure code into, say, a code word C1 to Cn. And for concreteness, think of this as being twice as long as the data. And now she computes the Merkle tree on top of that. The clients download the root, and the code word is stored on the network. Now, let's again try to make this unavailable and convince the verifiers or the clients that it is available. Now, to do that, because it's an erasure code, I need to oh, sorry. So what happens is the clients, again, sample random positions and try to download these positions and then verify the Merkle path, same as in the previous construction. So now I want to make this unavailable, but because it's an erasure code, I need to delete, say, at least half of this erasure code, if this is, for example, a Reed-Solomon code of rate 1/2. And then that means with every single query, I already have a constant probability of detecting this. So this is a much better system in terms of soundness. But still, I want to convince you that this is still not a good system. And for that, I will sketch an attacker Alice that breaks a notion that we called consistency. And what Alice will do is she will take two different strings of data. She will honestly compute the erasure code word for both of them, and then she will mix these two. She will take the first half from the first code word and the second half from the second code word. And then she will compute the Merkle tree and, well, store this mixed code word, which is not really a code word, on the network. And now let's look at what happens when the clients make their queries. Say we have the clients, they download the Merkle root. And now say there are some clients that just randomly make queries and end up just querying the first half. And maybe there are some other clients querying just the second half. And now we group these clients into these two groups. Then from the perspective of the left group, it looks as if data 1 had been encoded. Whereas from the perspective of the right group, it looks as if data 2 had been encoded. Okay, so in some sense, these two sets of clients have consensus on the Merkle root, but they don't have any consensus on the data. And that's very bad. If you have consensus on the block header, you of course want to have consensus on the data. Okay, so where does this problem come from? It comes from the fact that this Merkle tree doesn't really ensure that what you commit to is really a code word. It was in this attack, it was this mixed string of two code words. And for that reason, we introduced a primitive that we called erasure code commitments. And this primitive captures this idea that whatever you commit to is a code word. So what does that mean? Well, Alice has a code word, and she can commit to that code word succinctly to Bob, and then later she can open individual positions of that code word. Of course, you can do that with a Merkle tree, but the crucial security guarantee here is that whatever you open, it will always be consistent with the code. There will always be at least one consistent code word that is consistent with all the openings. That's an erasure code commitment scheme. And we then showed that data availability sampling can be constructed from this cryptographic primitive in a sound and consistent way. Okay, and then with this compiler, we looked at several constructions, as I already mentioned, and they roughly fall into two categories. The first one is based on a trusted setup with very efficient commitment and openings. And the second one is purely hash-based, but there, unfortunately, the commitment and opening size scales with a square root of the data size. And that means the communication for the clients now scales with the square root of the data size. And so this naturally suggests to look at the following question: can we have a construction without a trusted setup, maybe purely based on hash functions, which is much more efficient, for example, a polylogarithmic overhead? And this is what we tackle in this work. Okay, so that concludes the first part of the talk. I hope we now have some intuitive understanding of what data availability sampling is. And now let's look at the results from this paper, which is data availability sampling from Frye. Okay, so the first question is, what is Frye? Well, Frye is a fast Reed-Solomon IOPP. Okay, so it's fast, that's good. It's for the Reed-Solomon code. The Reed-Solomon code is an erasure code that uses polynomials, and it's an IOPP. So what is an IOPP? Well, it's an interactive oracle proof of proximity. What does that mean? Well, we have Alice and Bob, and they both have access to some code word that is contained in some oracle. And now Bob wants to be convinced that this string is really in the code, or to be more precise, Bob wants to be convinced that this string is close to the code. And Alice wants to convince him that it is close to the code, so they interact in some protocol. And afterwards, Bob can be convinced that this is close to the code. What does it mean to be close to the code? It means there's at least one code word C star, such that C star and C differ by, say, at most, in this example, one position, but in some upper bounded number of positions. Okay, and now you may wonder, why cannot Bob just look at all the positions and check it himself? Well, we assume Bob is restricted. Bob doesn't want to make too many queries to that oracle. That's an interactive oracle proof of proximity, and Frye is a very prominent example of that and a very efficient one. Now, if we look at these IOPPs, then you may wonder, okay, they look very similar to what I mentioned before with data availability sampling and erasure code commitments. So what is really the difference? And let's try to understand that. So let's look at some string C, and let's compare the guarantees that these two primitives give us. So an IOPP and an erasure code commitment. So an IOPP essentially just says there are only a few red positions, a few positions where the string differs from a code word. On the other hand, an erasure code commitment says something slightly stronger. It says that you can never open these red positions, right? It says whatever you open is consistent with the code. Okay, so still, when we looked at this, we thought, okay, there has to be some way to turn IOPP into an erasure code commitment. And this is what we did in this work. So we define, or we give a new compiler that turns IOPPs into erasure code commitments. Okay, so we want an erasure code commitment. To recall, this is, why do we want this? Well, we want data availability sampling. And in the previous paper, we showed that erasure code commitments imply DAS. Now, what we do is we define a new property of IOPPs that we called opening consistency. And very, very roughly, it says you cannot open these red positions. Okay, and then we showed via some efficient compiler in the random oracle model that IOPPs with opening consistency imply erasure code commitments. And then in the main part of our paper, we give an analysis that shows that the Frye IOPP, without any change, has this opening consistency notion. Okay, and then in combination, we get an erasure code commitment from Frye and then a data availability sampling scheme from Frye. Now let's look at this scheme and compare the efficiency to the other schemes. So as I said, there are these trusted setup schemes, which are very efficient, and the hash-based construction from the previous paper, which scales with square root of the data size. And now from Frye, we get a new scheme that scales with a polylogarithmic factor in the data size. Okay, and I want to say that this is not only an asymptotic improvement, this is also a big improvement in terms of concrete numbers. We have a bunch of tables in the paper if you're interested. And yeah, that brings me already to the last slide. I want to summarize what we have seen. I have explained, or at least I gave you an intuition for what DAS is, and maybe the important takeaway is you can construct them from these new erasure code commitments, and I think these are a very interesting cryptographic object to look at. And then we have seen the new contribution in this paper, data availability sampling from Fry. So this was a construction that does not have a trusted setup. It's efficient in a sense that it has a polylogarithmic overhead. And we achieved this by giving a new compiler from IOPPs to erasure code commitments. And that used this new property of IOPPs called opening consistency. And I want to end this talk by giving you something to think about, an open problem for future work. If you're interested in IOPPs, maybe you design an IOPP that is in some sense better than Fry. I've heard there's a best paper award at this conference that gives an IOPP that is better than Fry. And then you prove opening consistency. And then with our compiler from these two papers, you get data availability sampling for free. And that will make people in the Ethereum community happy, I guess. And yeah, that's it. Thank you for your attention.
If there are any questions, please go up to the mic or speak loudly.
Quick question. So in papers like the dispersed ledger system and others, there's this idea that you just collect pre-images from the Merkle tree and then reconstruct the whole code word and compare it to the root of the Merkle tree. And this way, if Alice is not committing to a code word, just discover it after the fact. Is there a reason why that doesn't fit into what Ethereum wants to do for this?
So you say I collect enough transcripts of these clients, and then when I have them, I reconstruct the code word, and then I look at the Merkle commitment, right?
Right. I reconstruct a code word, and then if that doesn't match the Merkle root that I got, then
and then what do you do then?
Well, you just say the message is bought, and then.
But then the system has a very bad liveness. Right?
Well, bot is what she committed to, so bot is what you open. I don't know if there are situations where that matters or it doesn't matter. Just in Alice now, it looks like a bad, and you not only that, but you know that Alice was evil because she.
It could also be that the network was evil, right?
Oh, because because the commitment is
okay, because the commitment is malformed.
Yeah. I mean, I know there may be situations where that's not acceptable. I just don't know like what, the bigger picture problem that needs to be solved here, like how, and
okay,
also depends on how big N is here as well. Like, but okay, that was my question.
Yeah, let me think about it offline, and then we can talk about it.
And Tal, yeah.
Yes, that is correct. And the XR consistency property roughly says that if you run the IOPP and then there's a closed code word, and then there are these positions where the thing that you committed to differs from the code word, then you cannot open, and what opening means depends on the IOPP, you cannot open these positions.
Compared to the coded Merkle tree or the 2D Reed-Solomon code for data availability sampling.
I didn't get
the
that.
Two-dimensional Reed-Solomon code for data availability sampling or the coded Merkle tree constructions.
So by two-dimensional, you mean the one where I take, so I expand my data in horizontally and vertically?
Yep. So the original constructions from.
So we have an analysis of that in the first paper.
Okay.
And you mean in terms of efficiency now?
Yeah.
Okay, so it's less efficient because the 2D Merkle, the 2D Reed-Solomon construction uses KCG commitments, and so it's more efficient, but it uses a trusted setup.
Okay.
Right, so it's like comparing snarks to Starks, like Starks maybe are larger, but don't use a trusted setup. The 2D thing in Ethereum, it uses KCG.
Yes, I don't know if it is used in Ethereum yet.
No, it's not.
Yeah. Okay. Thank you.
Okay, thank you. And with that, we'll get ready for the next speaker. Let's give a hand for.
Okay, sounds like it's working.
Okay, so our next new primitive will be pseudo-random error correcting codes, and Sam Gunn will be presenting the talk.
Hi, so yeah, I'm going to be talking about an object that we call pseudorandom error correcting codes. So, oh, I need to click. So this is based on joint work with Miranda Christ, who's a student at Columbia. Okay, so pseudorandom error correcting codes are a cryptographic object, but they come up very naturally in the context of detecting AI-generated content. Okay, so I don't think I need to convince you that being able to distinguish AI-generated content from like naturally generated or human-generated content is potentially a really important issue of today. But given that this problem comes from machine learning, maybe the most natural approach to solving it is to use more machine learning. So in particular, you can try to train an ML classifier to distinguish between like AI-generated content and human-generated content. Okay, so a lot of services have done this, but unfortunately, none of them really work that well. So actually, the New York Times has a survey on this from like a year ago, showing that without even like changing the images at all, a lot of the times you can get images that were AI generated that will fool all of the existing post hoc detectors, at least at the time of doing it. Okay, and you should only expect this problem to get worse because as Gen AI becomes more powerful, the content that it's able to generate should be more and more indistinguishable, if not statistically indistinguishable, from content that's naturally generated. Okay, so this is where watermarking comes in. So in watermarking, we try to modify the generative algorithm to embed a hidden pattern in the content that we can later detect. Okay, so what are the algorithms that we're trying to watermark look like? Well, any randomized algorithm can be written like this. It takes in some input, which in the case of Gen AI is like a prompt, and it takes some randomness, and then it produces the content, right? So a natural attempt to watermark anything like this is to change the randomness to make it some form of tampered randomness. Okay, now if you have some way of from the content computing an approximation to the tampered randomness, then you can try to detect the watermark as long as you have some way of distinguishing the tampered randomness from the true randomness. Okay, unfortunately, in all Gen AI scenarios that I'm aware of, such a randomness recovery algorithm exists. So given just like an image or like some text that was output by a model, you can recover an approximation of at least part of the randomness that was used for generating that sample. Okay, so you can do this, but there's a problem with this, which is that tampering might hurt the quality of the generated content, right? In general, whatever you're doing to the randomness to make it to get some pattern could change the kind of image that you're generating. So this is where cryptography comes in, right? In cryptography, we know how to reason about indistinguishability, and if we can get if we can use pseudo randomness instead of actual randomness, then we get the guarantee that the content that the thing generates is provably indistinguishable from content that it would have generated without the watermark. And in particular, we know that with respect to any efficiently computable metric of quality, the quality doesn't degrade at all. Okay, now we need a trapdoor for our pseudo-randomness to be able to detect it. Okay, so this is good. We solved this problem, but there's another problem, which is that randomness recovery is almost never perfect. So in every situation that I'm aware of, randomness recovery gives you, an approximation to the randomness you started with, but you'll be wrong on like usually a constant fraction of the bits. Okay, so this is where a pseudo-random code comes in. A pseudo-random code is just exactly what you need. It's pseudo-randomness with a robust trapdoor detection algorithm. Okay, so if you have such a thing, then you can just plug it in to any Gen AI algorithm that has a randomness recovery algorithm, and then you immediately get a watermarking scheme. And also, if your pseudo-random code can encode information, then you can actually encode messages in your watermarks, maybe like user IDs or timestamps or whatever you want. Okay, so just to make sure we're on the same page, let me give a quick, slightly more formal definition of a PRC or pseudo-random code. So a PRC is a pair of algorithms, encode and decode, that satisfy pseudo-randomness which is just probably exactly what you expect. It's like the same condition for like pseudorandom encryption. It says that if you encode messages, the responses are all pseudorandom. Even if you encode the same message twice, the responses should be jointly pseudorandom. And then error correction, which says that if you encode your message and then add a low weight error to it, then the decoder should still work with high probability. So here also, I wrote E has low constant weight, but what I meant is constant fraction weight. So like a constant rate of errors, and you should still be able to decode. And that's really important for the application to watermarking. Okay. So a couple of quick notes. For the purpose of this talk, I'm only going to consider binary PRCs and random bit flips. So binary PRCs is out of necessity for the applications, and random bit flips is out of simplicity, and also it's a bit, the construction, whether we get for like non-random bit flips is a bit subtle. Okay, also we construct, in this talk we'll see in a moment, we actually construct a stronger public key version of PRCs. Yeah, where you can make the encryption, the encoding algorithm public, and you still have pseudo-randomness. Okay, so how would you go about constructing a PRC? Well, a natural attempt is to just combine pseudo-random encryption with error correction, right? Because these satisfy the two properties that we want. But if you encrypt your message and then encode it, then it's not pseudo-random because the error-corrected encoding might have structure in it. And if you encode your message and then encrypt it, then it's not robust anymore because the encryption has no robustness properties in general. So by the way, you could think of this first thing as like robust encryption. It still satisfies semantic security, but not pseudo-randomness. And this other thing, I don't know of any properties that it satisfies. So, okay, but I really want to emphasize here that every code bit has to satisfy both pseudo-randomness and robustness. And this is what really makes this like, you know, from my point of view, fundamentally different from like either of these other objects. Like you can't just have like something that's pseudo-random and something that's robust. Like you need, every bit has to have both properties. And it makes constructing this thing actually pretty tricky. Okay, so but now let me tell you how we do it. So we're going to rely on LPN, or learning parity with noise. We're going to rely on like a sub-exponential variant of it. But LPN says that noisy samples from random linear codes are pseudo-random. So here, everything is over F2. A is like a random generator matrix, and then S in U are random vectors, and E is like a low weight, like constant fraction weight random error. Okay, so we're going to construct a PRC by showing how to sample a random linear code A with a robust trapdoor P. So we need the two properties that first, the marginal distribution on A should be uniformly random, because this is going to allow us to invoke LPN to say that noisy samples from the code are pseudo-random. And then we need that the information P, the trapdoor P, which is going to be a matrix, lets us distinguish the noisy linear samples from uniform. Okay, so the way that we do this key generation, the way that we do it is we're going to first sample a random sparse matrix P. So P is going to be a random matrix that's like slightly wider than it is tall, where every row is going to have exactly log n ones in it. And then we're going to sample a uniformly random matrix A that's going to be very skinny from the kernel of P. So in other words, a random matrix A that satisfies this equation here. Okay, and then the theorem that we prove is that if you do this, then the marginal distribution on A is negligibly close to uniform in statistical distance. Okay, so how do we use this to build a PRC? Well, you might already see it, but what we do is to encode 0, you output a random string. To encode 1, you output like a noisy sample from the image of A, right? And then by our theorem, the marginal on A is uniform. So by LPN, AS plus E is pseudo-random. So in both cases, whether you're encoding 0 or 1, you're going to get a random string or pseudo-random string. Okay, so we have pseudo-randomness. Now for decoding, all you have to do is just compute all the parities and see whether significantly more than half of the parities are satisfied. Right? If they are, then you know it's 1. If they're not, then it should be 0. Okay, and because of the low density, it turns out it's robust. You can make it robust to a constant rate of errors. Okay, I'm going to skip that. Okay, so that's how you encode 1 bit. It's natural to wonder, how do you encode more longer messages? Well, what we do is we're going to sample a random string U, a random string of like security parameter many bits, U1 through U lambda. and then encode each of those separately with our 1-bit PRC, and then use those random bits, the U's, as a seed for a PRG to one-time pad any classical error-corrected encoding of our message. Okay, so you just need any classical error-correcting algorithm that doesn't need any cryptographic properties, and then you can take a single-bit PRC and then wrap them together, and very easily you get a linear rate PRC. So yeah, and then for long messages, the information rate of this scheme approaches that of the underlying classical error-correcting code. Okay, so now that we have these, you can just plug these into this template that I showed you earlier, and you immediately get a watermarking scheme for any randomized algorithm, as long as you have a randomness recovery algorithm that's good enough to match your error rates that you can tolerate. So let's see some examples of what this actually looks like in a real, Gen AI setting. So maybe the simplest one is for generative image models. So modern generative image models work by mapping between some sort of latent space and like an image space. Okay, so you could think of the latent space as like a high-level representation of like images, like, maybe how happy is the image, et cetera. And there's some algorithm for going both ways between these two things. So the way that images are sampled from a modern, image generator is you sample a random Gaussian from the latent space, like a random multivariate Gaussian from the latent space. And then you apply this, map to get an image. So, okay, so the natural thing now that we have a PRC, the natural way to watermark it is we'll just, instead of sampling a random Gaussian here, you're going to sample a random Gaussian subject to the ith bit of the, sorry, the ith coordinate of the Gaussian having sign equal to the ith bit of a PRC. So basically just put it in like, one of the quadrants that corresponds to like the PRC code words. Okay, so now if you do this, then it's pseudo-random, it's indistinguishable from a Gaussian. But as long as you recover something with like a correlation with your initial signs, then you can detect the watermark. Okay, and indeed, we tried this on like Stable Diffusion and other like modern models, and it works pretty much out of the box. So this should be coming out in like a few weeks. This is with Shandong Zhao, who's was a student at UCSB, but now he's at Berkeley. Yeah. So this one, also just to show the breadth, I'll do this one really fast. You can also, this randomized algorithm that we're watermarking doesn't have to be like a generative AI algorithm. You could also think of it as being like a training algorithm. So now the inputs would be like the data, and the randomness is whatever randomness you used in SGD. So if you do this, then you can apply the same template, initialize the weights of the neural network to have PRC signs, just like we did before, instead of random Gaussian initialization. And then as long as training preserves some, epsilon fraction of the signs, then, or half plus epsilon fraction of the signs, then you can still detect the watermark in the weights of the trained neural network. So, yeah. Okay. And then finally, there's a line of work about watermarking for text. So we talk about this a lot in the paper. I won't go into detail about how it works, but basically, the way that you watermark text is to, bias each token that you're sampling towards, some pseudo-random bit. So in this case, we'll just use pseudo-random bits from a PRC and bias the text towards that. Basically, you can get text where the tokens of the text are just biased, or just like have a half plus epsilon bias towards some PRC code word. Okay, and if you do this, you get, so first of all, you actually, because you can get PRCs that are robust to constant rate of errors, we can get the first undetectable watermarks that are robust to a constant rate of errors on the text. But we can also get other corollaries like pretty straightforwardly. So for instance, public attribution is where you would like for the user to be able to to prove that a given text output was generated by a particular model. So it kind of has different criteria from regular watermarking, because in attribution, you want your watermarks to be unforgeable. So in particular, robustness is actually a bad thing in the case of attribution, right? Because if you can generate something from the actual model, change a few words to make it say something bad, then the watermark shouldn't still appear. Okay, so using PRCs, we show that you can get the best of both worlds. You can get a watermarking scheme that has both a robust watermark detector and also an unforgeable attribution detector. Right, so they have to be different algorithms because of the second bullet, but you can get them to both exist for the same scheme. So how do we do it? It's going to be super straightforward. So you start sampling your text. You sample the first like block of text with bias towards a PRC encoding of like 0 or whatever. And then for blocks after that, you sample them with bias towards a PRC encoding of a signature of the previous blocks. Right, so now for standard watermark detection, you just check is each block, is any block close to some PRC code word. And for unforgeable attribution, you actually decode the block, get the signature, and check that it's consistent with the previous block. And that'll be unforgeable by the unforgeability of the signature. Oh, yeah. So okay, so I think the takeaway is that it's a very simple template, and you just need this like simple mathematical object that's difficult to construct to instantiate the template. And you get, not only do you get the ability to watermark new types of media, you also get improved, robustness, improved and features for like existing situations, like public attribution. Okay. So I want to wrap up by mentioning some recent work and then a couple of open questions. Work of Golowicz and Moitra construct polynomial alphabet pseudorandom codes with robustness to adversarial edits. So it's not binary anymore, but now it's robust to like adversarial edits instead of just random edits, random errors. So this is a really cool result. Unfortunately, right now it relies, because of the polynomial alphabet size, it relies on like a crazy strong entropy assumption. But I think if you could remove that entropy assumption, then you would have, in my view, you would have basically solved like the theoretical side of syntactic watermarking for text. Okay, so another work of Cohen, Hoover, and Schoenbach define a notion of adaptive robustness for watermarks or for PRCs. So it basically says that if you that even if you choose your errors based on like previously seen encryptions or previously seen watermark text, you can't find an error that will remove the watermark or remove the or break the PRC decoder. Okay, and when they show that a previous scheme satisfies this property, but for very low error rates. So okay, so another upcoming work should be out in a few weeks also. We show that the scheme actually from this talk that I already showed you actually also satisfies this adaptive notion, this adaptive robustness notion for constant error rates. So and this I think is pretty cool. Uses some like coding theory stuff. So yeah, so I think there's a lot to do there. But let me tell you, I think the two biggest open questions for me, in my mind. So the first one is, can we construct a PRC that doesn't have quasi-polynomial time like attacks on the pseudorandomness? So because of the fact that we use these log-n sparse parities that I showed you in the scheme that I showed you earlier, there exists a quasi-polynomial time attack that will distinguish PRC code words from random. So I think it's a really interesting question of whether you can get one with like exponential security. And finally, are there other useful ways to tamper with the randomness used in machine learning algorithms? I think it's kind of an interesting way you can get cryptography in machine learning. So one example of this is this undetectable backdoors paper where they also do this kind of, yeah, but there's very few examples of this. I think that there should be room for more. So that's it.
We have time for at least one quick question.
You describe a bit by bit encryption for the pseudorandom code.
Are you talking about the linear rate boosting thing?
The LPN based.
Oh yeah, the bit
encryption scheme. But it seems like this would work for plenty of other like lattice based like IND-CPA encryption schemes. So do you think you could benefit from using something like MLWE or MLWR to reduce bandwidth?
So I don't know all of those particular assumptions that you mentioned, but I have tried a lot actually to do the same thing from LWE. Even that is non-trivial, but I think it probably can be done. But the issue is, two things. One, there's a kind of a different notion of errors when you think about error on LWE, right? It's like low weight on every coordinate usually, whereas LPN it's like you have an error on some bounded number of coordinates, and that which is kind of the more relevant thing for like error correction, I guess. And I guess the other thing is that it inherently would seem to have a large alphabet, which is I think really the bigger problem, because large alphabet schemes, like I wouldn't know how to get them to work in any actual watermarking application. I mean, I think they're really cool and interesting to think about, but I don't know how to. I think you need to get something binary or at least like low constant if you want it to actually be practical.
Gotcha.
But yeah, I think it's a great question of building it from more LWE kind of things.
Thank you.
Yeah.
Okay, thanks for the talk. Let's give him a round of applause and we'll get ready for the next minute. All right, for the last talk of the session, we will be learning about certifying private probabilistic mechanisms, and Zoe Bell will be giving the talk.
Hi, everyone. So I'll be talking about certifying private probabilistic mechanisms today. In particular, I'll be mostly looking at the case study of differential privacy. So first, a quick reminder on what differential privacy is. Our motivation in the setting is to allow for external analysis of sensitive databases. We'll have a database curator who holds records about individuals. We'll also have an analyst who wants to query this database, and we'll receive some sort of randomized answer in response. An example of the sort of query that might happen is how many residents of a given census block have income above a certain threshold. With differential privacy, we want to ensure that the answer given by the curator doesn't allow us to distinguish whether a given individual is in the database or not. In particular, we mathematically capture this by bounding the difference in probabilities of given outputs based on whether or not an individual is present using these epsilon and delta parameters. The use of differential privacy has increased a lot in practice from companies to also government bodies as well. But various issues have come up, of course, issues with incorrect implementations and bugs, but also issues around low transparency around what epsilons and deltas are actually being offered, and issues where these were actually changed unilaterally behind the scenes without data subjects necessarily being aware that the privacy protections were being lowered. In this sort of environment, we can think about turning to some sort of cryptographic certification to give guarantees about what privacy parameters are actually being given. In general, this also fits into a broader framework of using a cryptographic paradigm for regulatory compliance, where institutions have to prove to auditors in our favorite mathematical senses that they're utilizing mechanisms for trustworthiness, again expressed through mathematical definitions, at design time. So catching this behavior as it occurs instead of having to go back and try to suss out what were these privacy parameters, did they change or not, instead of just doing it as we go. So to contextualize this work, I'll go through the kind of existing trust models for differential privacy and then the one that we use in this work. What I've kind of just described to you is the standard centralized DP setting where we have a trusted curator. There are also some settings that consider a non-trusted curator, such as local differential privacy and multi-party computation approaches to differential privacy as well. But these also have another difference where in the centralized case, there is this one curator who has full access to the database, where in both the local and MPC settings, they actually achieve protection against the untrusted curator precisely through never giving a curator access to the full database unnoisy in the clear. In our setting of certified DP, we're going to not want to trust our curator, but we're also going to still assume that they have access to the full database. without any noise or anything like that. And so the question is, what can be achieved in this setting? First, it's clear that we can't prevent privacy violations altogether because the curator could always just send out the database that they have, but we can hope to detect these violations whenever they do occur. So in the rest of the talk, I'll go through the security definitions that we use in our paper, as well as one of our constructions and our example implementation. So first, to further clarify what is meant by certified differential privacy, again, we have these two parties, the curator, who will now also become a prover, and an analyst, who will now also become an auditor or a verifier. We're gonna have three properties that we want. First, correctness. Of course, if both parties are honest, the release should be differentially private. On the other hand, if the curator misbehaves and degrades the DP guarantee, the analyst should be able to catch this violation proportionally to the extent of the violation and raise a failure flag bot. In particular, this will degrade the DP guarantee additively in the delta factor proportionally to the probability of bot, because bot being output is inherently privacy violating. On the other hand, if the curator is honest, the analyst shouldn't be able to trick them into revealing information about the database, and the release should remain differentially private. So we achieve this guarantee using a new notion that we introduced that's more general, called a certified probabilistic mechanism. We're going to have some probabilistic mechanism which takes input parameters and maps them to a random output. For correctness, we're going to want that this output is distributed according to the agreed upon mechanism. For cheating prover soundness, if the prover deviates significantly from the mechanism, the verifier should detect. And in particular, their probability of outputting bot should be approximately equal to the total variation distance between the outputted distribution and the desired distribution. Finally, even if the verifier misbehaves, the output should be still distributed correctly as long as we condition on the output not being bought. And along the way, it should continue to hide the prover's input. So to clarify this definition, I'll show some kind of graphs giving examples. For correctness, of course, we just want our standard correct distribution. For cheating prover soundness, what this means is basically the only thing the prover can do is move probability mass from some potential output and move it directly to bot. So the only way they can cheat is by increasing their probability of being caught by the same amount. Finally, in the cheating verifier soundness case, if we ignore the bot outputs, the distribution is just entirely correct. And this asymmetry between the prover and verifier is due to their different information that they have in this situation. I'll also just quickly clarify what we mean by hiding in this context. Of course, we could use generic techniques to add zero knowledge to our constructions later, but for differential privacy, all we really need is witnessing distinguishability. In particular, for a given output, we just want that the view of an adversarial verifier should be the same no matter what the underlying database is. And intuitively, this makes sense. So this is all we would need, because in differential privacy, we just want that statistical closeness, which is what witness indistinguishability gives us. So before I go to the construction, there's one more ingredient that we need, which is something that we call a random variable commitment scheme. The idea that we want here is that we want to be able to commit to a random variable that's drawn from a particular distribution without revealing what the value of that random variable is. For instance, we can think of drawing a permutation of a card deck uniformly at random in order to play a card game. We have a dealer and player who are shuffling the deck together. And again, we want three things. First, traditional binding. The dealer should only be able to open the resulting commitment to a single value. Hiding, the player should not learn what the commitment is to. But thirdly, we also want distributional soundness, where the dealer and player are both convinced that the commitment is to a value that's been drawn from the correct distribution, again, without the player ever learning what the specific value is. So now that we have this primitive, it becomes easy to see a construction for a broad class of probabilistic mechanisms called additive noise mechanisms. In this context, we'll have a distribution that's independent of the particular query in the database. And we'll just take the true answer to the query and add noise drawn from this distribution. So for this kind of probabilistic mechanism, we can get a certified probabilistic mechanism as follows. In our setup, we'll commit to the database in some way, and then we'll also generate a random variable commitment to the noise. Then when a query comes in, we'll convert our commitment to a commitment to the true answer, f of d. And then we'll use additive homomorphism of the chosen commitment scheme in order to add in our noise. Then the prover can just open the resulting commitment without revealing either the true answer or the noise individually in a convincing way. So to give a little bit more of a concrete sense of what these random variable commitment schemes can look like, here I have a diagram for an example with just a simple random bit commitment where we want to do a fair coin flip. I won't go through all the details, but essentially we just do a variant on coin flipping in the well with a Sigma protocol thrown in. And in that process, we're able to just have 3 rounds of interaction and a public coin protocol. And something to note here is that this sort of scheme will have to inherently be interactive to some degree, because if it was non-interactive, the prover could use rejection sampling in order to distort the distribution arbitrarily without getting caught. So this kind of level of interaction is as good as we can hope for. But then this also brings up a question of what public certifiability could look like in this kind of context, given that we can't use like the standard approach of non-interactivity to get public certifiability. And you can also think that like a lot of these DP contexts, we don't just want the one person who was involved in the original query to be convinced that DP was provided, but anyone who wants to go and check it. So public certifiability seems to be really important for this sort of context. And so our suggestion for this is that, as I just noted, our verifier in this case is just entirely a public coin. It's just entirely a public coin protocol. All we need to do is send some random bits. And so if we have some sort of trustworthy source of these random bits and some appropriate time stamping of messages, we could get public certifiability for our schemes. In particular, we might use something like the NIST interoperable randomness beacon, which offers this kind of high quality public randomness as a utility for these sorts of like auditing and transparency contexts. And so another way to think about our random variable bit commitments is that they're a way to turn this kind of trustworthy public random bits into trustworthy private random bits that can be used in contexts like differential privacy, where the noise remaining secret is essential to the application. I'll quickly go through an example of this instantiated for a certain class of queries called counting queries. Here we have some arbitrary predicate, which could express something like the income of the individual is above a certain threshold. And we're just going to sum up this count over everyone in the database. It turns out that in a lot of DP contexts, these are a very useful and important class of queries. We can release this sort of query using a simple binomial mechanism, which is an additive noise mechanism with a mean adjusted binomial added. And you can notice that both the counting queries here and the binomial mechanism are very additive in their structure. In particular, we can take our random variable bit commitments and utilize the additive homomorphism of our commitment scheme to get a random variable commitment to the binomial that we need. And so, oh yes, and I forgot to note that the parameter n of the binomial is just based on the epsilon and delta of the DP guarantee that we're looking for. But finally, yes, because we just have this additive structure, it turns out that we can get away just using very lightweight cryptographic primitive of the additively homomorphic commitment scheme, such as Pedersen commitments. Finally, I'll go through an example that we did with our implementation of querying income on a census microdata set. We had a few thousand individuals in dimension 37. And we set our privacy budget to be 1 and asked the query of how many individuals have income over a certain threshold. When this query is expressed as a polynomial, it has degree 6 and sparsity 63, which ends up playing into the complexity of our scheme, as I'll note in a moment. And in this case, we had a commitment time, one-time commitment time of a couple minutes, as well as randomness generation time of 500 milliseconds. And then once we got to the actual query, it was only 1.9 milliseconds. So now I'll just note that in general, like what the complexity looks like for our scheme. In the commitment phase, we'll have 3 rounds of interaction that can be made non-interactive with fiat Shamir. And the number of cryptographic operations will scale as the size of the database times the number of monomials in the query polynomials we'll be interested in later. This could be as many as 2 to the d, but depending on the application, could also be a very tailored set. And this only needs to happen once for an unlimited number of queries later. Next, for random bit generation, we also have 3 rounds of interaction, but this time we can't make them non-interactive, and it's just a small constant number of operations for each bit. And the total number of bits, again, only depends on epsilon and delta and not directly on the size or dimension of the database. However, this step will need to be repeated before each query. Finally, the querying phase only has, it's just completely non-interactive, and the number of operations is independent of the size and dimension of the database. It only scales based on the sparsity of the query polynomial. Here you can see some diagrams that show that this complexity scaling is reflected in our implementation. And for instance, that as we increase the query sparsity a lot more, we're still operating within a few milliseconds at query time. Finally, I'll just quickly summarize these contributions of introducing the DP trust setting of certified DP, this certified probabilistic mechanisms guarantee, this primitive of random variable commitments, as well as our constructions for additive noise mechanisms, this proposal for producing trustworthy private random bits from public random bits, and a particular instantiation for counting queries with binomial noise. Finally, we also implemented and evaluated the protocol. So some future directions that we're currently working on include certifying differentially private machine learning, data deletion from machine learning models or machine unlearning. There are also some probabilistic mechanisms for fairness applications that seem potentially interesting, and I'd be interested in any other probabilistic mechanisms that come to mind that might be interesting for this sort of application. So thank you guys for listening, and I'll open up for questions.
Hey, just a quick question. Do you assume that the server is committing to the accurate database in the first place?
Yes, so we do verify that it's well-formed, like the commitments are well-formed, but we do assume that that is the party potentially collecting the information, and they have the ability to commit to whatever valid database they want to.
Any other questions? Yeah, I had one more question. You talked about potentially removing interaction using a public randomness source. Why couldn't the prover just do rejection sampling by just delaying and using a different instance of whatever the source is?
Right, so you would have to timestamp the messages, and that the prover would have to commit to their randomness before the next message from the public randomness source.
Okay.
So it's like from the ordering that you would prevent that.
Okay. Thanks. If there's no other questions, that's it for this session, and let's thank our speaker one more time.